All right. Okay, good evening, everyone. You're welcome to physics class. From the last class, we talked about position and distance,
Sorry to
of
cut you.
course.
Sorry to cut you, sir. You
Yeah.
can either share your screen or work with your board.
Oh, it's fine. It's fine. It's fine. Okay, let me work with both. I don't want to share my screen because I have. Okay, so I will use both. Okay, all right. It's fine like this. So we are in physics class. Let's talk about physics. Okay. All right. The science subject, of course, definitely. And it's a branch of science which actually majorly deals with quantities or objects in relation to energy. All right. So anything we study in physics is how to derive energy from concepts or phenomenon or situation or anything, so that we can actually conserve our own human energy and tap into the energy of other objects or situation in order to gain maximum comfort. Fine, like that. And that is why we study objects, mostly different objects, and we study how we can derive energy from situations that occur both naturally and artificially. So on the concept of distance and time and velocity and motion, we are going to be talking about majorly motion. All right, so let's start from motion. In your biology, you will have been told that movement is a major characteristic of living things. So people move, things move. Everything majorly moves because physics makes us to understand that everything moves. Yes, everything moves. So most times when you base your judgments on the fact that because something moves, it is a living thing, you'll be wrong. All right. But it's one of those characteristics that we can use. All right, it's not the only. So let's talk about motion. Under motion, of course, motion simply means movement. But in physics, we define it as change in position in relation to time. The change in position of an object with respect to time. All right. So I can move. How long have I moved? All right. How fast is the movement? How slow is the movement? How far have I moved? All right. So when you consider all those things, you'll be considering concepts like speed. We'll be talking about vectorial positions, which is called displacement. Yeah, displacement. And you also talk about the concept of time. All right. But now, I will just try and break things down in a way that will be simpler for everybody. An object moves from one point to another with a particular direction of movement. That is called displacement. Displacement simply means, okay, let me take away this. Displacement, there are some concepts that are very interesting that we need to discuss under physics. One of them is displacement. To be displaced, you see, the word displaced means you are moving away from one point to another point. Under displacement, there must be two things you are measuring. And what are those things? You are measuring how far you have gone, and you are measuring in what direction of movement have you gone. So when you're talking about displacement, you are not just talking about distance, direction of your movement. And so a concept or a phenomenon like displacement is referred to as a vector quantity. It's a vector quantity. All right. Displacement is a vector quantity. It's a vector quantity. So I can have something like this. Can you see? So there's a direction I'm following to get to point B. I don't just arrive at point B from point A by disappearing and reappearing. I arrive at point B by taking a particular distance measured, particular direction measured in degrees. So two things. Displacement is distance moved in a specified direction. The direction has to be specified. So when I'm going 20 kilometers, in what direction? Is it in, and all of that. Thank God For you to be a student of physics, you must have been well versed mathematically. So you can't be a student of physics and tell me you don't know anything about math. So bearing and this, know the direction you are going, you will know how far you are going. That's called displacement. Now, the interesting thing about it is that displacement, you can use letter D to measure it, D, and it is measured in meters. Displacement M, okay, D is the symbol for the unit meter. So it is measured in meters. So don't confuse my D and M. D simply means displacement. Most times, some textbooks will use X. It's still the same thing, but it will be steady. All right. So don't confuse it. But displacement must always be in two reference of measurement, in terms of length and in terms of direction. So keep that handy. Then distance now itself. What is distance? The area covered by an object in motion. The area covered by an object in motion. So let me use another board to display that. Distance now. Distance. Distance is that you move from point A to B, just like we moved. No particular direction in focus. You don't need direction. You just need to get to B from A. How you get to B is none of our business. All right. Whether you follow a particular direction or not, we are not concerned. All right. How does that mean? Let me show you. So I will have used, let me use another ink to demonstrate that. Can use something like this. Okay. It depends on, okay, I can do this. I can move from A to B because it's the distance. I can go like this, At least you know how our road is in this country. You are going somewhere and there is no shortcut, or most times what you call shortcut is not actually. I've gone this way, this way, this way, this way, this way. No particular direction in focus. All I am saying is that I left A and I arrived at B. Okay. So the issue now becomes, how will I be able to do this? Actually create a kind of quadrant that will cover all the areas under my movement. And once I'm able to do that, then I can measure the area that is covered in that green box. Those are the B. And when you have this, you can also call it meters, because definitely it is measured in meters. So distance is also D or X, which is also measured in meters. Somebody will measure in meters, number one, because it is not actually that to cover the entire area. We are only using that area as a demarcation of the limit to which you can move. All right. Because of the reason that whenever you are engaging in movement, believe that it can be any part of this area that you can cover in moving from point A to point B. And that is why distance is also measured in meter. Definitely, we know you pass through some point. So it can be A to point B, just like what I have in this red dot, or this time around, let me use C to D. Okay, so it is also measured in meters. So when you are considering distance, direction is not considered. We don't need direction. It's none of our business. So that is the concept of displacement and then distance. So once these two are clear to you, of course, it is measured in meters. Once these two concepts are clear to you, we can now that distance is a fundamental quantity. Distance is a fundamental quantity, all right? Distance is a fundamental quantity. I need you to note that. It's one of those 7 fundamental quantities that we discuss in mathematics, all right? Subsequent classes, we need to discuss some basic, out of all these fundamental quantities, we still have some basic fundamental quantities, which are called LTM, time and mass, anyhow you want to call it. Anytime you measure a phenomenon in terms of length, mass, and time, you say that you have a dimension. So we'll talk about that in classes to come. So I'm building on the concept of displacement and this. I'm not just moving without considering the time it will take you to move from one point to another. So your movement in terms of time, depending on whether you are moving in a particular, you are covering a particular distance in a particular direction, which is called displacement, or you are just copying a particular discourse next. Let's talk about the concept of velocity. For velocity is displacement over time, the rate of change of displacement with time. I want you to get this clear. Velocity is the rate of change of this is equal to d over t or x over t. I told you that displacement can be d or t depending on what they use, depending on the particular concept or notation that anybody uses, but I can just use that interchangeably. So it can be d over t, which means displacement over time. It can be x over t, displacement. All right, so we have that. It is measured in meter per seconds. Time is measured in seconds. Now look at the way I'm writing it. This is the way it should be written. Don't write it as meter per seconds. It is not that when you write it like this, it is meter per seconds. Meter, displacement is measured in meter, time is measured in seconds. But to represent the IUPAC nomenclature of units representation is why you write it as this. I'm going to caption that in green box, units in physics, all right? Because you know that when you have something over divided by its raised to power minus 1, all right? So this is the standard way of writing units in physics. IUPAC nomenclature also applies to not only physics, but also chemistry, possibly biology too, I guess. So, seconds. Then, what does that mean? I'm going to give you the graphical representation. When I have something like this, let this represent my D, displacement. Let this one represent my T, the time. Now, the rate of change of displacement with time is increasing. As the distance is increasing, time is increasing. You are having increased velocity. You are having increased velocity, all right? This is, of course, I can fix that one just simply here. If you have it this way, the velocity is reducing. As the distance is increasing, time is reducing. All right, so you have it like this. You have it like this. This is reduced velocity. You have a special type of velocity, which is called uniform. Because definitely on the road, when you are driving your car, you don't move at a particular speed, throughout the whole journey. At some point, you slow down. At some point, you speed up. At some point, so when the rate of change of displacement with time is constant, that's what we call uniform velocity. So I can demonstrate something like this for you. And when the velocity is moving, this is uniform velocity. The rate of change of displacement with time is constant. At some point, it will be like you are covering remains the same, but time is changing. So velocity here is zero. Velocity here is zero because, you are just on the same distance. That is, time is changing, but distance remains. The displacement remains. At that point, you are not moving. You are not velocity at this point, at this section. Let me use blue marker to demonstrate. Velocity at this section here, V here, is equal to zero. All right? Because distance is zero. Definitely we've demonstrated, displacement is zero. Then at some point, the time still increasing, you discover that your displacement is reducing. All right? This is T, this is D. Okay, so for this one now, you have the velocity is reducing. All right? And then you have, when you stop moving, velocity is zero. So I can demonstrate through here. When you start from zero, you are moving, velocity and time is changing gradually. At this point where I started circling with blue, your displacement remains zero because you are not moving. All right. And then time is changing. Of course, time is changing. Velocity is zero here. And then at this point, you start reducing your displacement. So you have something like this. I'm only compressing all of this information, okay, in a way that will be easier for you to understand. Okay. When you use this diagram I'm giving you is called displacement time graph. That is, there is a whole lot of similarity between this and the next concept I want to talk about, and that is speed. For speed is the rate of change of distance with time. The first one I mentioned, velocity, the rate of change of displacement with time, change of distance with time. So that tells you something about velocity and speed, that they are not the same thing, almost the same thing, but not really the same thing. What's the difference? One is the vector quantity. Automatically, velocity is also a vector quantity. Now, for speed is the rate of change of distance. Distance is a scalar quantity. It is only one reference of measurement that it needs or it requires. So speed is also a scalar quantity by default. So speed, I will also use V to represent speed. That's why I'm saying there is a whole lot of similarity between them. But it's always good that you know that they are actually not the same thing in practice. They might be they can use interchangeably speed and velocity to mean the same thing, but in practice they are not the same thing. So keep that handy. So speed is rate of change of distance with time. It is also measured in meter per seconds. It's also distance with time. The same level of diagram that I have for speed works for velocity. So you have speed like this. You also have what we call uniform speed. The word uniform is the same. The rate at which you change is the same. That's when you say you have uniform speed. And then, of course, at some points, you are going to have your uniform speed. At some point, your speed becomes zero when you are not moving. This one is for distance. It is called speed time graph. This one is speed against time, speed time graph. I'm going to demonstrate some things to you. And then this one is the downward movement. Let us demonstrate something interesting. When you are throwing a stone, what will happen? Because I saw a question in JAM that was asking that question. You throw up a stone, and I want you to look at this very well. As it's going, time is counting the distance that is covered because it's a particular. Let me just do a layman interpretation. A stone will go up and then will come down. This, because when you throw a stone up, you are only looking at the physical trajectory based on your own observation. You are forgetting that there will be a time that is counting from zero, from the time you throw that stone up. So it will not follow this one. So this will not apply to it. Let me use another color now. Let me take away this. All right. So it will follow. This is my distance covered. This is my distance covered. So when I throw up something, I expect that as the distance is increasing, time is also increasing. And I'll get to a point momentarily to stop and it to start coming down. It is coming down. What it means is that distance is reducing. I'm still at the point where I throw up the stone. When I threw it up, the stone is moving away from me. That is and a car is moving. Let me draw that. A man is here, and then a car is here. All right, just pardon my cow. Very fine car like that. Once this car starts, the man is here from that man. So it has an increased distance. But when the car is reversing, the car is coming back to the man. So the distance is reducing. So that is the past question. And people are picking wrong diagram. This is the exact diagram that represents the trajectory of the stone. When you throw a stone up, and then they are saying they have some diagrams that represent the right diagram to show the distance against time. People are picking wrong diagram, but this is what it should be. The distance is increasing, but when it gets up, it cannot stay up. That is why you don't see a time is counting. So there cannot be a reason why the stone will continue to stay up. The stone cannot stay up. So it will be almost immediately, momentarily, the stone will start coming down. Reduced distance, but so please note, this will be the correct, when you throw up a stone and then it comes down, this is what will happen. So far, so good. In the next 4 minutes, I believe we have distance. We talked about velocity, and now I've just discussed speed. Speed is the rate of change of distance with time. It counts. Okay. All these definitions are necessary. It is after that we cannot begin to talk about equation of motion. But then we won't talk about equation of motion if we have not mentioned acceleration. Acceleration with time is increasing. You say you have acceleration. When the rate of change of velocity with time is decreasing, you say we have deceleration, or what you call negative acceleration. So most data says the rate of change of velocity with time. So let me demonstrate that here. Let me take this away. So we say acceleration now. Acceleration. Pardon my writing on the acceleration. Acceleration is represented by A is the rate V over T, not speed or velocity. Though they can use velocity and speed interchangeably, but majorly acceleration is the rate of change of velocity with time. Now, acceleration is measured in meter per second square. Acceleration is measured in meter per second square. Because why? I can quickly demonstrate that if time permits. I hope time will do. Because we say velocity, distance over time, which is meter per second, all right? Which is meter per second. I'm sorry. Yes. Not velocity I wanted to mention, actually. I wanted to mention, speed, velocity. Yes, I was right. What's wrong with me? I was actually right. Velocity is the rate of change of displacement with time. Velocity is the rate of change of displacement with time. Now, acceleration is the rate of change of velocity with time. So I can write this as meter per second square, meter per second over seconds, so which becomes per second, something like this. And of course, you have -1 plus -1, so it becomes meter per second square. All right, that is why you have that unit. Displacement, we've discussed distance, we've discussed speed, we've discussed velocity. Now we are discussing acceleration. Our time is almost used up. Let us stop the question you are free to ask. Next class. illustrations. Even for acceleration, there is a graphical illustration. Acceleration is as a result of velocity against time. You can plot the graph of velocity that to you. Please note, very important. Anytime you plot the graph of distance against time, the slope of that graph, if it is distance against time, the slope is speed. But if it is displacement against time, the slope is velocity. Let me come again. If it is speed against time, just like we have time, sorry, if it is distance against time, d against t, then you have what I called speed, distance against time. So distance time graph, we always talk about speed, while velocity, all right. So the same way, when you have velocity time graph, what you are going to be discussing is acceleration. So if this one is v, if this one is velocity against time, so this a, so probably we will dedicate next class to discussing the details of all these graphs, and then probably if we have that time also next class, we'll also use that to discuss the concept of what each of these things I've mentioned, and I'm going to list them out on the next one. So we talked about d or x to mean displacement or distance. We talked in speed or velocity. Now we are talking about a to mean acceleration. Don't forget that distance or displacement can be measured in meters. Speed or velocity can, while acceleration will be measured in. So I want to stop here. If there is any questions so far, let me know. When an object, okay, not moving, velocity is zero. When an object is not moving, velocity is zero. All right. It is only when an object is moving, because an object is not moving. When you say distance over time, there is no distance covered. Anytime an object is not moving, no distance is 1,000 seconds or 2,000 seconds, it doesn't matter. Zero over anything will give you zero. That's why velocity will be zero. And the same thing, when an object is not undergoing any form of velocity, acceleration is also in velocity. Acceleration is automatically zero. So all these facts are actually what JAMB is testing. JAMB is not going to ask you the definition of things. It's application of concepts. You can apply it to solve questions that come, just like I just showed you concerning the graph of a stone that is thrown up. And then they use a graph to illustrate the movement of the stone to determine which will stop. And if there is any question, you are free to relate them with me. Practice question around this topic, and the next class will take it from there. Thank you very much. I'm done.
Thank you, sir.
You're welcome.